Good evening, everybody. It being a little bit after 6 and people in Hobart generally being late or not attending, we'll get this underway. First of all, I'd like to thank you all for coming. This is a seminar sponsored by Wood Solutions, and I would ask people during the break if you could just sign in on the registration sheet, please. Tonight we're talking about prefabrication options for timber structures, finishes and fittings. So the program for this evening is that I'm going to give an introduction on prefabrication, what it is, what it includes. We're then going to look at potential for prefabricated timber structures with Fred Boswell. Fred is a director of Truss. We'll then have a break, so there's tea and coffee out in the next seminar room for people. That will then look at advances and opportunities in digital design and computer-driven fabrication, because the prefabrication of larger elements is actually now being mirrored by a lot of prefabrications that's driven by digital design and routers. And Matt G, who's project manager for Prefab Lab, will talk about that. And then I'll wrap up with a short overview of the NRAS inverse module construction, in that it's a form of prefabrication of large-scale modules, for those of you who haven't seen that project, but it does round out the work that Fred and Matt will talk about. So I think as we start, I'd like to begin with a definition. And that is what prefabrication is. So it's the design and off-site manufacture of a project-specific component, assembly or system that's utilised in part or as whole to build a structure. Now, key things about that is that it's done off-site. So you're not making it on the location where you're going to use it. Being built off-site means is that you have greater potential for quality control. It doesn't mean you'll use that potential, but you've got it, because you can do things in a controlled environment. You're making the piece to go into a project, so it's not a commodity. It's not like a piece of plywood that you buy at the shop or a pack of pine. It's something where someone's made a decision and cut a component that can go into your building. That also implies then that it's more precise than what you've got on site construction, because you're making it to a size that's determined by the design, and that you're then transporting that thing from some location where you've made it to the site where you're putting it together and putting it in place. Now, you may make parts of it in one location, assemble it near the site and then lift it up as a component. So we can look at some of those things as we progress through. Now, a prefabricated thing, when people talk about prefabrication, there's a lot of confusion, because some people will talk about a prefabricated building and someone will talk about a prefabricated truss, and people think, I mean, how can they both be the same thing? So we've put together a matrix of prefabrication. So effectively what we're talking about is that you can look at various dimensions of the component. We call them 0, 1, 2D and 3D. So with 0 you've got a node that you make and you use then to put things together. With a 1D you actually take a stick of some description and you pre-cut, pre-shape, pre-prepare that stick, and you bring that stick to site. With 2D, you're actually making some form of panel or flat component, which then you're going to assemble with other similar flat components to make a three-dimensional structure. The next is you can actually make a module or a volumetric item, which then you can bring in to stack, put next to each other, etc., as the basis of your building. Now that's the bottom axis, and if we go up the chart on the vertical axis, we can actually increase the amount of finishes and layers and detail that we put into the component. So a simple nail plate truss is at the bottom end of the complexity in the 2D panels. We can actually make a whole floor component, which we could call a 2D unit, but it can then have many of the floor trusses in it. It can have a floor in it. We could start to insert services. We can make wall units that have increasing levels of finish and services in them. So we can get complexity as we go up. We can make a simple box, or we can completely finish the box and then deliver that whole finished box to site. So when we talk about prefabrication, it's important to then identify which ones of these things on the matrix we're actually talking about at any one time. So Fred's going to predominantly talk about, I think, he's going to talk about this sort of area. Matt's going to talk about some in this area and some in that area. The NRAS project we're going to talk about, it's up the top up here. But they're all prefabrication. They're all different approaches to prefabrication. And if we start to think about each of these things, we can start to feel that we can... Prefabrication offers lots of options, no matter how individual or how standardised the building. Now, prefabrication implies forethought, that you've actually worked out everything, but it doesn't necessarily mean that you're constrained to some restricted system. So if you start to think restricted system prefab, just get that out of your mind, because most good prefabrication allows lots of freedom, but at the same time should allow a lot of benefits because you can do it in a controlled situation. So if we just look at some examples, this is a 1D element. This is a prefabricated glulam element that actually ended up in a building built for the Sydney Olympics. It was all cut to size, perfectly arranged, arrived on site, and then was just bolted into place. These are 2D elements. These are ganged nail plate trusses put in location in the School of Architecture building. So you can see that that's a 2D bit, and all those 2D bits are then made into some 3D arrangement. This is another type, a slightly more advanced or more complex type, is that these are panels from a house factory in Northern Europe, and in this, all the windows, all the insulation, the cladding and everything is on, and all these things are then stacked up so that you've got a fully locked up house in a day. All the load-bearing components are there. So you bring it in, it's all done, and everything's insulated in. Now, it's the same as the nail plate truss, conceptually, but it's just got more layers of finish that goes into it. And this is our volume. So this is the NRA, one of the modules designed for the NRAS project. This is the prototype. It was manufactured and tested. We drove it around, and this is it being loaded off. So this is the type of thing we can fit into this site. Okay, so there's notable exemplars of prefabrication and timber prefabrication in Australia, but timber prefabrication is still a relatively underdeveloped art in Class 2 to 9 building in Australia. And that's one of the reasons to hold this seminar, is that we want to develop that art. So.
Good evening, ladies and gentlemen. I'm probably going to take you through the simplest forms and getting to fairly complex structures that we can do tonight. Basically, our simplest form of prefabrication is basically grabbing 2 sticks of timber and lengthening them. And basically this type of prefabrication is gone out the door because products like high span and high joists, etc., have taken over from those type of prefabrications. And then we see on-site situations where you can either do this as a panelised and lift it into place, or make it together on site. Simplicity of, continuous length members, such as this, and with high span, and you can slip your insulation in while it's being constructed. And then we've gone to a storage building, and as you'll see there, we have fairly chunky pieces of timber, but that's also because we've done a lot of commercial loads to it as well. And then we get to steel web floor trusses, which today are starting to take over, or even from the timber ones. And the reason that they're taken over is commercial factor, which is that they're around about $3 to $4 a linear metre cheaper to produce and place in the marketplace than the full timber ones. So I'm just calling out some of the realities of what we're facing every day with our customers. And don't hesitate to interrupt me and ask questions as we're going through. We often think of timber as the end-all and be-all solution, but I think without steel and concrete, we wouldn't be able to achieve a lot of the building design that we need to do today. So this is basically floor trusses sitting on a steel ledger bolted to a concrete wall. And this is timber to timber connection, timber to steel connection. And the beauty with floor trusses are that piece of timber that you see diagonally going across the trusses is what we call a strong back, which distributes a point load from, if there's a point load on one truss, it distributes it to 2 or 3 on either side. So you get good performance out of it. And we also do floor trusses and put Hebel concrete floor panels on them, etc. So we take all of those types of things into consideration when we actually do the design. And that's looking underneath at a Hebel floor, sitting on timber trusses. And we also use them in roof structures. This was a building that we did out at Smithton for the School of Agriculture. At the rear end we had about 3.5 metre cantilever of the roof structure, and that's that same area that we're looking at there. And on the sides we had a 2 metre cantilever, and this is the building while it's being erected. And at the front we had a 5 metre cantilever. And beauty with these type of projects is that I was called in by the architect and the engineer at the design stage so that we could try to solve some of their design problems and give them solutions of how we could, the products that are available in the marketplace, and also put it together so it was doable. There again, steel webbed floor trusses as roof purlins. And this complete roof structure was all done out of what we call floor trusses. They were spaced as purlins at 600 centres, and that's the end result of, they obviously went across the building, not lengthways. There we have a building with floor trusses, roof trusses, rafters, so the complexity doesn't have to be just one element. There are quite a few different elements, and as you can also see on the right-hand side of the building, we've cantilevered the floor out, which is supporting walls which are load bearing. And then we also do prefabricated framing. And these are just some shots of prefab frames in situ in our projects, some commercial, some residential. Embrace the hell out of it where it's required. Now we get into roof trusses. This is the Hersey Seafood up in Stanley. That was the job once it was completed. And this is it under construction. Basic high span trusses, painted up. The nail plates basically disappeared. That was it. And we can do quite lots of complex shapes, scissor trusses, as you see in these photos. Complex roof shapes, stub heights on the ends of trusses, beam pockets so that we can hook onto beams, etc. Roof trusses coming into girders, which are then supporting other trusses as well. And complex ceiling shapes. This was a job that we did down the Huon, and you'll notice on the front left-hand side there was just a very sharp roof slope, and the architect had designed that to take solar panels. So we cantilevered those trusses out and applied the solar panel loads. So cantilevers of 3.5, 4 metres with roof holes in them. Shape for box gutters. And you'll notice that on each truss we also have a nail plated upright so that the builder doesn't have a hinge joint when the cladding goes up. And he frames in between each truss to accommodate cladding. Just showing you some photos of what it looks like. This is a building called The Shed in Bicheno, and you'll notice solar panels, etc., on the roof. And this is the building inside, and we had exposed high-span trusses spaced at 3.5 metres, and also no bottom cord ties. And this is one of the things that I'm always fighting with engineers about is, generally speaking, that they want bottom cord ties in at maximum of 3 metre spacings, etc. But we've been kicking a few goals where we don't require them in these kind of situations. So it would have spoilt the look of this building inside, I reckon. This is a fairly large residential property that we did in Launceston. That's looking at the bottom end up. That's looking at the top end down. And you'll see there's a lot of different angles, roof shapes. We had box gutter sections. We had sloping ceiling sections, etc. And as you see here, we've got a girder truss going along because there were a lot of windows in this building on the front, and they actually acted as a lintel for the roof support. This is the Opera House in Ulverston. I'm just showing you something. I'll call it the Opera House because of the peaks in this roof. Girder truss supporting, a large ridge beam coming in. We also do things such as prefabricated box beams in truss form, etc. Yeah, we'll get to that. Not a problem. This is the Penny Royal refurbished when they were basically pulled a lot of the old buildings down and reorganised it. And this was just a commercial job where we supplied the trusses, worked with the architect and the engineer on the design, what was achievable. If you have a look at the bottom chord slope that we have there. And fairly large openings in the roof onto a courtyard, and we just go around with girder trusses, parallel girder trusses, so we can achieve the shape that the designers wanted. And we get some weird and wonderful things that we have to try to manufacture in our factory. Large cantilevers, and the striking thing about this was that, generally speaking, rule of thumb is whatever you cantilever, you've got to have twice the backspan, but we got multi-node engineers onto it, and we could do it. And I got the builder to jump up and down right at the end of that cantilever, and we had probably 1 or 2 mil deflection out of live load. Also do prefabricated dressy trusses. Expensive items though. Truss like that, you're probably looking at about $6,000 a piece. Trusses hooking onto large beams. Truss to truss connection with a truss boot. And then tie downs. You can see the different types of tie downs. You've got a heavy duty one there, and then you've got the multi-grip or triple grip next to it. And then talking about prefabrication, of trying to educate the building industry to consider, wherever they can, fabricate roof or roof panels onto the ground. This project was for a building called Chicken Feed in Lagana, and I'm just going to give you some figures and sums. The builder estimated that it was going to cost him close to $100,000 to erect these trusses ready for cladding. And I said to him, I reckon we can halve it very easily. And he wanted to stay conservative, so he said, I'll allow $60,000 for it. And this is how we made it up in sections on the ground. And at the end of the project, I asked him, what did it actually cost you in total, with the crane hire and your labour and all the rest of it? He said $28,000. So, you know, sometimes it is a matter of educating your customers of how it can be done.
How big was that area?
I think it was around about 1,100 square metres. Yeah, plus occupational health and safety, doing it on the ground rather than up in the air. This is the UTAS accommodation. Sorry, Greg, I'm stealing some of your thunder. This was quite an interesting project because at the end of this, the high side of the building, we had a 1800 cantilever, and we had to allow for, because it was 3 stories high, we had to allow for 19 tonne to be hanging off the end of the truss to accommodate the 3 walkways that are going to be hanging off it, 3 levels of walkways. So it was very challenging, but it was, in the end, it was fairly simple. So these are the modules being built on the ground, being lifted up into position. This is with the cladding on. Small crane brought it round from where they prefabricated it on the ground to a position where the large crane then took over and lifted it up into position. Then to make sure that it was a nice, snug fit, it was ratcheted together against the first module. So basically we're, you could say 4 stories off the ground. From an occupational health and safety aspect, it was a good result. Talking about curved roofs, we don't actually do curved trusses. What we do is that the top chord is segmented and the roof battens are put in at 1/4 of the panel distance every time, and that way we can get a perfect radius as you see there. Sorry, going the wrong way. Can't remember. Curved beams. We don't actually fabricate them, but I do source them for customers and clients.
Tell me where?
Where I source them from?
Yeah.
Yeah, from either Melbourne or Brisbane.
Okay.
Yeah. And some of them want to turn them upside down. Getting back to trusses, this was a project that we did in Port Sorell for the Port Sorell Community Centre. And the largest span across there was 28 metres. And the original design was done out of 900 by 135 GL18s. But when we actually tried to source product, because they had to be in one length, wasn't possible to be done because the longest length we can get is 16 metres. So I suggested to them to consider maybe doing it in trusses and applying plywood, and we applied a 15 mil layer of plywood, which gave us the fire rating that we required for 2-hour fire rating, and from there all the rest was done in trusses at 1200 mil deep parallel trusses. This is in our factory, manufacturing them. This is the base plate that we concealed in the bottom of the columns. So there were 3 layers of 45 mil trusses, and we had these steel dowels, and those steel dowels were then accepted a bolt which we set on the base plate. And these are some shots of the building as it was going up. So 28 metre long rafter with 15 mil ply. But the ply was there, did help structurally, but was basically there as a fire rating.
Is that steel there as a haunch? Like a strong haunch?
That, yeah, well, that was just, it was a combination of steel and the building itself is done on what we did, and all the rest of the steel in between is just basically an infill for their cladding, etc. That was the entryway into the building in its final stages. I haven't got any shots of the inside of the building completed, but that's the outside of the building completed. We also did a church down in Ranelagh a few years ago, and there again prefabricated much of it on the ground and then was lifted up into position. Just showing you some shots of the same position to give you an idea of what it looked like completed. That's our steel, the 50mm steel dowels going through, and then obviously they're bolted from underneath. But we do that type of thing in our factory before it goes out. Pool cover for St Mary's District School out of high span, and it was just painted up to give it a little bit of a non-industrial appearance. This was for the Bridport Community Hall. And we started off with 8 degrees roof pitch on one end of the building to 8 degree opposite roof pitch at the other end of the building. Heavy plywood gussets, they were 32mm thick, F27, and just screwed connection. There was an 18-metre span across that building. And this is our new factory that we're currently building down in Cambridge. We got all the components together for the walls, laid that out on a grid line on the floor, and then we've built the roof structure over top of it. Just to give you some shots and ideas of what we've done here. And we've put the cladding, roof cladding on it, and you'll see that the rafter, the column is hanging off the actual rafter of this portal frame.
Is there any cost comparison, like commercially, to steel?
It's very hard to know exactly, but around about 15-metre span up to 24, 25-metre span, I know we can be very competitive with steel. I'm not going to say, I know on some projects I've been, on a building this size, well, I'll be $30,000 or $40,000 more economical. And on others, when they find out that I'm competing against them, all of a sudden their steel prices drop. So this is a little video of before it was lifted. And the next morning, 6 o'clock, the cranes arrived on site. Some shots of it as it's being lifted up. And by I think at 6 o'clock in the morning they arrived, 1:30 the last crane drove off site and the building was standing. This is just a short little video of the actual lift. Yeah. I reckon the builder who's actually doing it for us, he reckons he probably saved himself $20,000 on labour, and considering the scaffolding and all the rest of it that he would have required. So, the cranes were $8,000 for the day, but when you consider occupational health and safety, how simple it was, it's a little bit of planning beforehand, but did the site measure on a job where we had to do an extension to a building. This was a girder truss spanning about 10 metres, and it was carrying about 10 metres span of other trusses. Can we blow in on this at all, Greg?
Sorry, Fred, no.
Okay. But single plate, and that top, the top plate of that wall had a rather large fracture in it. So my suggestion was that the builder put a macro prop under there straight away and make sure that there's a couple of load-bearing studs underneath it. So, and basically that concludes my presentation. Thanks very much.